Hello everyone. So I'm presenting the project report of MC211. So in the first question, we are given a Celsius temperature equation lying in the XY plane, and the distance are measured in meters. Like there is a particle which is moving in a clockwise direction around a circle with radius 1 centered from origin, and it's moving with the constant speed of 2 meter per second. And in this first part, we are supposed to find how fast the temperature is experienced by particle, like changing in degrees Celsius per meter at a given point. And in the second part, we need to find the Celsius per second at the same point P. So we all know that we can convert the point in a vector form, like just doing the I cap and J cap. We are studying linear algebra course as well. So I converted point P in the displacement vector form, and we know the equation of circle will be x square plus y square equal to 1, since it's a unit circle kind of thing. And we also know that it's moving with the constant velocity, so the direction vector, that's the velocity, like you can say the direction vector of the particle at a given point is same of the velocity vector, and it's always perpendicular to the displacement vector of that particle. So using that concept, we can find the direction vector. So we can say that P was the displacement vector. I found the vector P, that was the displacement vector, and slope of that P is nothing but √3. And through using this √3, we can find the direction or the slope of our direction vector. That's the both are perpendicular. So using that method or mathematical formula, we found the slope of a velocity vector. And we also know that we can, like using the one point and the slope, we can divide or derive the equation of line. So here I derived the equation of line, and using this equation we can also find the intercepts. Like I found intercept on y-axis, and also I got 2 points. So like the main motto is to finding the unit vector, like in the direction of movement. So using these 2 points, I can find the vector which is in the direction of my motion of the particle, and this is the magnitude of this vector. And using these two things, I can find the unit vector, that's the direction in the direction of my motion of a particle. So I got that thing, unit vector, and from the given equation, I can find the gradient of temperature, like gradient at the point P. And we know that from the formula, like this is nothing but kind of like degree Celsius upon the uh, upon the distance, like kind of thing. So we just need to substitute the gradient and the unit vector we found earlier. So using that, we got the temperature per meter. And now the particle is moving with constant velocity with 2 meter per second. So we know the magnitude of V is 2, and here is the, like in the second question, we are supposed to find the Celsius upon time, or Celsius upon second. So temperature upon second. So here is the equation, like you can write in the del T by means dou T by dou X into dou X by dou T in the form. This form, if you see clearly, then using the rule of dimension, we can clearly see that temperature Celsius upon time. And already in the other question, we have found the temperature upon distance, and we also know that the velocity is having displacement upon time. So you can say that we can cut out the displacement kind of thing, and we just remain with the Celsius and the time. So using that logic also, we can solve this question. So I use that thing, like multiplied with the magnitude of velocity and found the unit vector again, and the dot product of this earlier found the temperature upon distance into the distance upon time. So we got the Celsius upon second thing, which was supposed to find. So it's 1.87 degrees Celsius per second. So the second question also, it's like more like a similar form, but here we are given the parametric question in the form of t, x, y, z was given in the form of t. So using that, first of all, you found the gradient. Here it's quite easier to find the unit vector, so I'll say in later on part. So here I found the gradient at a given point 8, 6, -4, and the particle was moving. So we can write in the gradient like parametric form. We can form the equation, And by comparing the point and these x, y, this thing, we can easily figure out the value of t, like at which time t we are supposed to find whole the displacement thing. So here we got t equal to 2. So differentiating the equation of particle, this is nothing but the equation of our displacement. Like in the earlier thing also we have found the, in the earlier stage we have found the displacement vector. Here it's in the form of parametric form. So differentiating that, we got the velocity form, and substituting the t we got the velocity equation, and we also found the magnitude. And using these two things, again the same thing, like this is the velocity and this is the magnitude, we found the unit vector, that's the direction of motion, and doing the substitution of gradient t and this direction vector, and doing the dot product, we found the answer, that's the temperature. And in the second part as well, as explained earlier, we will just do the multiplication with like the dot product with our velocity, magnitude of velocity. So we got 736 Celsius per second is our answer. In the second section, we are supposed to find absolute and relative and the percentage change questions were given. So in the first question, I just used the, to estimate volume of radius. Things were given, radius and height. Radius was 2 meters and height was 3 meters. And how accurately should we measure radius and height? So the error estimate of our volume is that doesn't exceed 0.1 meter cube. So, and also there was given dr is equal to dh, like possibility in error. So here is the given statements, and we know using the like predicting change of differential, like from x naught to y naught to x naught plus dx plus y naught plus dy, like the differential part. So df by this equation we can write simply form, and here we will change it, like we are having, instead of f we have volume, and instead of x and y we are having r and h. So here is the new formed equation for our problem. Here is the partial differential of differentiation of volume, like v is equal to pi r square h. So vr would be 2 pi rh and vh will be pi r square. Similarly, vh also we can find out. Then just substituting the in the equation, and also using the term like dr was equal to dh, it was already given, and this we ended up getting this, and we are to not exceed 0.1 in the error of dv. So just using that concept, we can substitute from here dr into 16 pi, and dr would be 0.1 upon 16 pi. Also, you know, the dr was equal to dh, so this is the final result. So radius and height should be measured so that this error isn't like increasing from 0.0198, and approximately we can say 0.002. And in the second problem, we have to find the like which term, like we are given the economical problem somehow. So it was economical quantity of goods, radio, shoes, brooms, whatever, like from the store, and there were factors like k, m, h, and we need to find the sensitivity of each, like q is dependent on, like more sensitive on which variable. So we can use the direct change in variable concept here as well. So just the same as in the earlier part we did, like instead of f we have q, dq. So df would be turn out to be dq, and here we have 3 terms. Earlier we were just x and y, so we can like increase into 3 dimensions as well. So here we have 3 terms, so we can put it in the 3, we can modify equation. So qk, qh, and qm, we found out the qk, qh, and qm by doing the partial differentiation of this equation which was given earlier, and substituting it, we got the dq. Now putting, we have also given the points like k, m, k naught, m naught, and h naught. So we just kept that point in equation, and using that we can like kind of predict, or you can say kind of get an idea like on which the changement factor. These are the changement factor dk, dh, and dm, which are more like making dq more sensitive to that part. So in the end, we got that DH is having the coefficient like of 800 value, like, so it's highly like sensitive. H is the most sensitive variable of Q. Like even the small changement in H will lead to like huge compared to DM and DK. So Q has highest changement with respect to H. Then comes the Lagrange multiplier. Like the first question was cheapest storage tank. We have to design like a tank of volume 8,000 meter per cube already given, and in a such a way the customer asked us to make like use the least amount of material we should use in building the tank, and we should recommend what should be the height and the radius of our cylindrical part. Like a tank was a cylinder, and on top of the cylinder there were two hemispheres. So volume of cylinder would be a cylinder, hemisphere, and hemisphere. You can say the hemisphere will be sphere. So use those equations. The surface area of cylinder and the sphere and the cylinder. So we are supposed to minimize the surface area. It's subject to volume. So we know the formula. Like first we found the gradient for of surface area and for the volume. And we know from the Lagrange multiplier that we need to minimize S with respect to, or you can say with the given constraint of V. So we use the formula and we need to find the lambda, the coefficient, by equating the coefficients of I and Z terms, the gradient before. Sorry. So by equating, we got two equations. In the first equation, we got this whole thing. And in the second, we got that lambda was equal to 2 by R. So we just substituted in the first equation and we found that H is equal to 0. Like we are knowing that R by R would be 0, and R was earlier given that it can't be 0. You know that radius, since this cylinder can't be formed having 0 radius. So R won't be 0, and hence we can cut out this R by R equal to 1. And we ended up getting that height is 0. So actually we not require like cylinder. We would just get like it was hemisphere and the cylinder part. So height is 0. That means that we have just ended with a sphere of radius R and volume 8,000. So using that like sphere and the volume formula, directly found the radius. So we have recommended the value like height should be 0 and radius should be 10 into 6 by pi to the power 1 by 3. Now the hottest point on a space probe. A space probe is like it's kind of it's moving in the ellipsoid, enters like in the Earth's atmosphere and surface begins to heat in the form of like it's moving ellipse. And after 1 hour, the temperature of the probe was given with this equation. And we need to find the hottest point on the probe surface. It was the ellipsoid kind of thing to suppose. So here we need to maximize the this temperature of the probe with respect to its shape. So we first found the we are given both equations. So we first found the gradient and then applied the Lagrange multiplier. We need to maximize T, like the temperature with subject to constraint of SAP P. The given equation we just equated I, J, and K. It was given in the I, J, K form. So 3 equations. Got 3 equations, and from this we found like 2 cases. Like from the first equation we got that either x are not 0. If x are not 0, then we can simply cut out and we got lambda equal to 2. And x can be 0. Like there were 2 cases. If x is equal to 0 or x lambda equal to 2. So case 1, when x was equal to 0. So if x is equal to 0, then from these 2 equations we can like find, like we can just do the division like 2 by 3, and we can cut out the lambda because lambda is not 0, can't be 0. So we got this equation, and now we substitute this equation in the equation of our shape. Like I can find, where is that equation? Here is it. So this was the equation of our shape. earlier given in the question as well. So substituting the value of y and z, we got a complete equation in the form of y. Like from this equation, you got in the form of y and z, and substituting the z term in the p, like the shape equation, and x was already 0. So we got the final values of y. We got 2, like 4, y can be equal to 4 or -2. And for each y, we will get z's value. So when y was 4, we got z equal to 2, and when y is 2, we got 2 values for z. So in total, we got 3 values when x would be 0. Now the case when x isn't 0, but it's non-zero, so we can just cancel out the x term, and we got lambda equal to 2. Substituted in the equation 2 and 3, we found that y and z are equal in the from this equation, and in the further equation we found that y and z are equal to -4/3. And now substituting again this y and z's value in the shape equation, we got the values of x for each, like the same y and z, we got 2 values of x. So in total, we got another 2 points. So we have 5, we obtained 5 total points. And out of those 5 points, this 2 point gave the highest, and they both gave the same temperature, that was 642. So the hottest point on the surface of probe were 4/3, -4/3, -4/3, and -4/3, -4/3, -4/3. So we obtained 2 points. Here is the another section, that was the Taylor's formula. We need to create the things using the Taylor's formula. It's going to be a wonderful thing. I pretty like this part. So we want to plan, like we are planning to calculate the volume inside this stretch of a pipeline, which was about 36 inches in diameter and 1 mile long. So with what, like, should we be more careful in measuring the length, or we should be more in the diameter, and why? We need to give the reason. So we are given the pipeline. I've just stated things in the feet, like be common both in mile and inches. So for the gender conservations, or you can say conversions. Also, I made it in the radius for volume, because we have volume in the form of radius pi r square L. So just I substituted in r. Here's the Taylor formula. We all know that. So substituting, like the changing things were changing A to R, B to L, and the changement H and K with the changement values that are the delta R and delta L. So here is our Taylor's formula. I'm just taking till the quadratic because afterwards some things like in the third term they become more 0. So it's like okay to go till the quadratic approximation, and the error term is here power 3. So these are the calculations, like differential, partial differentials, and the values obtained for that part. So putting the values were given, like diameter and each. So putting the values, we obtained the approximation, quadratic approximation of volume in terms of delta R and delta L. Also, we found the error term in the form of delta R and delta L. And we are assuming that because everything, like it's completely dependent on R and L. So assuming that our error is also a constant. It's not like kind of like change. When we know that we would just assume in the rectangular portion throughout the open rectangular region centered at point AB. So here I consider it's the constant thing. So no need to worry about the C, like C is 0 to 1. So the main motto is here, we need to find the sensitivity of whether it's more sensitive on R or whether it's more sensitive on L. In the previous section, we have found, like we did 2 problems of the similar kind of concept, you can say, but using the other method. So now we can do one kind of verifying, like you can clearly see that we have R, delta L, and delta R square, and on the side of L we have just delta I. So clearly you can find that delta R is dominating. Also you can see from the coefficients, Like it's having the higher number compared to the delta L part. But we can also verify by putting the values. Like taking delta and delta R and delta L as same, like changement would be same, like 0.5, just changing 0.5, like doing error in 0.5 in the radius and doing the same error while measuring the length. So we found that if we increase like 0.5 in R, we are getting this much amount of feet volume, and with the same amount of changement in length, we are getting this much. So clearly you can see that radius is more dominating and more sensitive, like volume is more sensitive to radius. So we should be more careful in measuring the diameter of our pipeline. And the next question was about the electrical circuit. So there was a drop in voltage, like from 24 to 23, and drop in resistance as well from 100 to 80. And we need to check whether I increases or decreases and about how much, and also the same thing, like what the I is more sensitive towards voltage or resistance. So we use the Taylor concept. Here are the delta value, initial condition like V naught 24, delta -1, R naught 100, and delta R -20. Substituted in the Taylor's formula. Here too, I took the quadratic approximation. This is the error term. We need to check or see about the C part as well. So here is the substituted value C. This is the error part. I substituted these were the calculations and the values obtained. So I just put it out here. This is the changement in I, C, like first term here. So delta V plus, V naught plus delta V and R naught plus delta R subtracted by V naught R naught. So we get changement plus error, put the error, and keep it the maximum bound, like we are taking the maximum error, like that should be the maximum, but always you will get the lesser compared to that. But to keep highest bound, we are just taking the maximum. So for that purpose, we will take C as 1 in this equation. So for getting the maximum error, and I haven't shown the calculation because it's quite calculated, this whole problem of Taylor's. So we get this error when we take C equal to 1, and if you take C equal to 0, we'll get this value. And taking C equal to 1 because we want the maximum error, substituted in the equation we obtained here. We found that like the current will increase with 0.0493 ampere by changing the voltage and resistance. This is the kind of approximation. The complete thing in Taylor's are like more on the approx kind of thing. So this will be that. You can get more precise answer or more like changement, like taking the bigger terms. So here we got the error part, included error part as well, and this is the I value at the delta R and delta V. Here also we need to find the changement to like sensitivity. So the same procedure, I take the changes in voltage and radius with 10 kind of thing. Changement in voltage with 10 and changement in voltage with R with also 10. I increase both things. So firstly I do changement in R, and I obtained that I gets increased by 0.2184, and with the same procedure, like I took the voltage, increment in voltage, and I found that it's increasing more, like the increment of I respect to V was more, delta V was more compared to R. So I is more sensitive to the changement of voltage compared to changement in resistance. Now comes the vector calculus part. I did the linear integral. Like if you are a material engineer and you want to find the mass of a wire that was running on a plane road, let's say having density given, and there is a curve or line segment from A to B. So first I found the parametric equation from point A to point B in terms of T. So is that, and then just put it like we know the formula for mass of a wire obtained and given density. So put it in the, like this is the equation of parametric form, dx by dt, dy by dt square. This is the density in the form of xt and yt. So associated with that, xt, yt, and you know that it's in the parametric form. So we associate in the form of t. So sum here, and then this has the calculation part, and approximately the mass of that y will be 30. And then we found the formula, like we can find the surface area as well. So suppose there was a carpenter and who wants to compute the surface area of a portion of paraboloid lying above the plane, such a kind of plane, like assume it to being xy plane, because we have equation in xy plane. So this is the xy plane, and we have the paraboloid having the equation z equal to 25 minus x square minus y square. We need to find the surface area of this first part lying above the xy plane. So here is the equation for surface area in the form of, this is the equation in the parametric form, convert. So, or directly also you can go. So you just take z, dz, like dou z by dou x and dou z by dou y, bring in the formula. Now I took the parametric form, like and change dx by dy into r dr d theta. We know that r is the region bounded by the circle, like x square plus y square equal to 25, and we found the parametric form, and theta will be from 0 to pi by 2, like it's whole circle, so 0 to pi by 2. And I rewrote the equation in the parametric form and calculated, and area come out to be pi by 6, 101, powered with 3 by 2 minus 1. So in this part, the method of separation of variable, like there is an architecture engineer and he wants to find the trivial solution of a given equation, like which he will use in for designing the material in further. Also specifically mentioned that he want to find it using the method of separation of variables. So here is the given equation. We know that we can write P, Q, and T, like it's nothing but dou Z by dou X, dou Z by dou Y, and similarly T is also be Z by Y. So now we were asked to find solution using the variable separable method. So here we are taking Z as a kind of composite, like kind of thing, X, using x and y, where x and y are two independent functions, such that x is a function of x, all the x terms, and y is a function of all y, both are independent. And now we can write p, q, and t in the form of capital X and capital Y. So we wrote here p in the form of x and y, like dou z by dou x, so x dash y, and q would be dou z by dou y, so x y dash, and t was z by y, so x y double dash, like differentiating twice with y. So now taking these three terms, like pq in the form of y, x, and y, and putting in the original equation, we got this kind of form. And now we can separate both like x terms and y terms, and let's say there is constant lambda, and we compare with lambda and we get two equations, one in the form of x and one in the form of y. So first in the form of x, we got this equation and we just modified a bit, and finally on integrating both sides we got that x equal to c to e to the power lambda x. And now comparing the second, that's the y and lambda part. So we just modified this equation, y double dash minus y dash plus lambda y. And now taking the assumption that y is equal to e raised to my. So y dash will be e raised to my, y double dash will be m square e raised to my. Now substituting that in this equation number 2, we would get this part of thing, we separated e to the power my from all the terms, and we know that e raised to my can't be negative, can't be 0. So we left out with the 2m square minus m plus lambda would be 0, and that's the quadratic form. So we can solve using these methods, and we got m has 1 plus minus under root 1 minus 8 lambda by 4. Now we ended up in a condition, like there can be three cases. Like in the first case, when lambda is equal to 1 upon 8, so we end up getting under root part 0, and m has 1 by 4. Second case, when lambda is greater than 0, we would go in the complex part because it would be under root in the negative form. So m would be in the complex part. And the third case, when lambda is less than 1/8. So under root part would still remain, but it will be positive. So not in the complex, it will be in the real part. So we go for the first case where lambda is equal to 1/8. So at that time we get m as 1/4. And here we write the equation a e to the power m y by e to the power m y. We know from the ODEs concepts, just x and y, we know that both are independent, so we just took both and multiplied. Similarly for the case 2 where lambda was greater than 1/8, things were going to be in the complex part. So y a to the power y by 4, that's m by m was this thing like 1/4 still. The complex part, this whole thing under root 1 minus 8 lambda. So we got this equation, and both were independent. So just we did this multiplying, and there is another condition where lambda was less than 1/8. So it will be in the real part. So we get 2m. So one with the positive sign and one with the negative sign. So -1 plus under root 1 minus 8 lambda y, and -1 under root 1 minus 8 lambda y by 4. So we just did the same thing. Y. So in total, we got 3 equations, like 3 non-trivial solutions for our given equation. So engine would be satisfied with this thing. Now next comes the vibrating string problem. So there is a musical artist who is strumming his guitar and with some given initial conditions. Now he wants to find the equation of string at a given time t. Like for the given IVP, we can solve the thing and we can give him the equation what he want to get. So we know the general equation, like comparing this with given initial conditions, we found out the alpha would be 2, L is our pi. So this is the thing, L is our pi, alpha is 2. We want to find an and bn. We also know that this is the f of x, this is the f of x, like f of x and g of x, comparing with this whole part, like summation part of sine and bn. So sine bn cos bn sine part. So when you compare this equation and this equation, like by comparing the way that we choose the coefficient, like the like terms, so we got that a3 is equal to 1 and b10 will be equal to -1, and the rest of the other n are 0. And similarly, we can go for bn, like comparing with this equation, and we get 2bn sine n x, and we got two things like 4x, 6x. So we got b4 is 1/4 and b6 is 1/12, and rest other bn are going to be 0. Now taking this an and bn, we'll substitute in the solution for our vibrating string and get the final equation. So we'll start with this 3. A3 will get 1, b part would be 0. So 1 cos n is 3, alpha is 2. So cos 6t and sine 3x. So cos 6t sine 3x. Similarly for b4, now we go for b4. A would be 0, b4 sine 4 into alpha was 2. So bn would be 1/4 sine 8t, and again sine multiple will be sine 4x. Yeah, 1/4 sine 8t sine 4x. Similarly for b6, and then for the a10, and similarly we got the final equation for our vibrating string. So yeah, that's it from our side. And like I really enjoyed in finding the problem and solving this. Like it helped in like making more sharpen some concepts, and was really good opportunity for us. And also if one thing like speaking for half an hour, it's really a good thing to do. Like it's difficult task, so we appreciate for you sir and ma'am. So thank you.